my goodness. My friend told me that when I go sliding down the ice, I age slower. Is that true? Oh, physics penguin, you got some cool friends. Sliding down the ice sounds really fun. We call that glissading. Yes. When you move faster, time moves slower, or time stretches relative to folks that are not moving. So for a penguin that is standing still on the ice, their time is moving slightly faster than a penguin that is sliding down a big long ice slide. How do we know that? That is a wild statement, right? That time is relative. Let's dig into it. Okay, so first, we are going to use some diagrams to show reference frames. So our first reference frame that I'm going to put over here is an experimental setup that we can use to do some math on. And for this one, this is going to be a stationary setup. So our penguin is, ooh, black and white. Penguins are black and white. I don't have black chalk. I have brown chalk. Okay. So we have a penguin. Let's see if I can draw a penguin. Sure, that's good enough. Okay, there's our penguin. And our penguin is gonna have a flash of light because we need to keep things simple here. So let's say there is a mirror and our penguin shines a flashlight that releases some, well, I guess it would be on the other side of the penguin. It releases some light. That light travels up to the mirror and then it travels back down to the mirror in a straight line. And the distance that that light travels is from here to the mirror, and this distance is a distance of d. And also because we are good scientists, we're going to label our axes. So this is y, and this is x. I'm also going to give these a prime notation, and you'll see why in a second, because we're going to have multiple frames of reference, so we need to be able to keep them apart. So now we can ask some basic questions, like how long did it take the light to travel a distance d? So we know that the speed of light is c, and that is just a velocity, and that is calculated by the distance that it travels over the time interval that it has traveled. And so because we're getting a little bit serious here, we're going to use delta t, which just means time interval, or you are measuring the time difference between 2 points. Just like distance, basically. It's the distance between 2 points. The time interval is the time distance between 2 points. And so this is going to be 2d divided by c. And we can see clearly because it travels a distance d upwards and then a distance d downwards. So the total distance that it traveled is 2d. I might say that this could be y here because it's moving in the y direction. Okay, so that is the time interval for our stationary frame of reference. But now let's say we have a penguin that is sliding down the ice, and we're going to need a longer frame of reference here. We're going to go like that. Okay, so now our penguin, I'm just going to draw a circle this time. There's our penguin. Okay, and our penguin releases the same flash of light. And for our experimental purposes, we're going to put our penguin in a box. La 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 la. Okay. We'll give the penguin a head, I guess. That's a weird. Okay, I like my circle better. Maybe we can just give it like a beak like that. I like that. That's cute. Okay. But now I want to give it a little tummy. Okay. Okay. We're having some fun here. So this is the same kind of situation where you have a mirror at the top and a flash of light. But now our penguin in a box is moving along at speed v. In this case, I also want to say that this happens at x1, and we'll say prime. So this happens at a location, whoopsies, not prime, x1. And as the box is moving, this the box in a distance in a certain amount of time will be over here. Our penguin will be here. Our mirror will be here. At another point in time, the box will be over here. Penguin, mirror. And our light, according to an observer here, the stationary penguin, the light is going to travel like this. It's going to bounce off the mirror, and then it's going to bounce back to the place that it started where the penguin is holding it. Let's give our penguin a little beak at least. Doop-a-doop. Okay. All right. And the point in space at which the light returns back to the flash, we'll call that x2. Now, the same distance, oh, I lost my white chalk. There we go. The same distance between the mirror and the flash of light is d. Same distance. This is really important. But now our light has actually traveled a longer path. Hold on, that's wild. If it travels a longer path, but the speed of light is always the same, it's a constant, the speed of light is 3 times 10 to the 8th meters per second. That never changes. So if our light is traveling a longer path than it did when it was stationary, then it must mean that the time is longer also. What? Because if you increase the distance, the time must also increase to cancel it out. Think about it. Like if you have c equals 2y over t, you're not going to get the same value for c. So you have to be equivalent. It has to be 2y over 2t. So can we actually check this? Because that is a very, very bold statement, my friends. That the time, the length of time must be longer in this situation than for this situation, for the light to travel. In other words, the penguin will experience a stretching of time. So yes, we actually can math this out because we can use handy dandy triangles. So I love triangles. So we're actually, yeah, let's use white. So we can draw a triangle here, and we know that on that triangle, we have a distance d. We don't know what this distance down here is, but we can say that, let's say that this is, I don't know, this is halfway, h half, and we can use the same equation for velocity. We're gonna go all the way over here. So velocity is just x over t, where x is the distance traveled. Oh, I almost went out of frame. Okay, from frame of reference, out of frame. So x half is just gonna be v times delta t over 2, because again, this is halfway. This is half of the path that the light has traveled, and this is the other half. And the triangles would be the same. So then this would be x half, which equals v delta t over 2. And then the hypotenuse of this triangle is going to be the distance that the light traveled. So we'll say x light. And that is going to be equal to c, well, let's just x light equals, we do the same thing with the equation, but this time we have c instead of v. And we are solving for this distance. So we multiply t times c, and so it's going to be c delta t over 2. Oh no, my chalk broke. Again, because it's half of the time interval. Excuse me. Okay, so now we have, and here I want to be clear, let's add these primes. So we're going to say that this frame of reference is, oops, no, this is the regular one. Okay, just kidding. So this should be t prime. So t prime is stationary, not moving. No primes, moving. Okay, our penguin is letting down the ice, so no primes on this one. Okay, and now we can ask, because we have some things that are related. Okay, so we can ask, how can we get to a point where we can compare delta t prime to delta t moving? All right, so now we are going to do some mostly algebra math. Okay, so bear with me. We're going to use some triangles to help us out. So triangles. The hypotenuse, a squared plus, hold on. a squared equals b squared plus c squared, where a is the hypotenuse. So you have, I'm running out of space here. Okay, so we'll do it over here. Okay, so the hypotenuse is going to be c delta t over 2 squared equals d squared plus the two sides squared. So this is going to be v delta t over 2 squared. And now we just do some algebra and solve for delta t. All right, so bear with me. You can speed this up if you don't want to go through a bunch of algebra. So we get c squared delta t squared over 4 equals d squared plus v squared delta t squared over 4. We move all the t's to one side and we pull them out. So we get delta t squared. Actually, let's multiply by 4 first. So we multiply everything by 4, and then we get 4d squared, and then we move them over. So we are going to get c squared minus v squared equals 4d squared. So all I did was I multiplied by 4 to get rid of the fractions, and then I subtracted both sides from this, so I moved them over. And then delta t squared equals 4d squared divided by c squared minus v squared, and then we take the square root of everything, and then we get 2d over root c squared minus v squared. Okay, and that is what delta t equals. We can write it in a little bit of a simpler form, which would give us delta t equals 2d over c. Well, I should say we want to do a comparison. So if we pull out a factor of c squared, then we get 1 over root 1 minus v squared over c squared. So we can pull the c out, and that's what is left, because this comes out nicely, but we have to divide by c squared to make sure everything's equivalent. Okay, so then we can substitute delta t prime, and this is where the magic happens, because I'm gonna try to do some color stuff. Okay, so then you get delta t. We're getting close to being squished. Delta t. Okay, I am gonna erase our algebra because we have the important bits. So delta t equals, this is the same as this, so we can substitute in delta t prime times 1 over root 1 minus v squared over c squared. All right, QED, what's up? So this means that the time interval in the moving situation is longer than the stationary situation by this factor. And sometimes we call this factor gamma in relativity, because if you go learn more about relativity, that factor will come up a lot. It is very common, and you can kind of think about it as a ratio of the speeds. So we are going to define, we can also delete our little triangle. So we are going to say that gamma, we're just defining terms here because we want to be lazy. And anytime we see the same type of formula come up, we can pick a Greek letter or some other letter, or we can make up a symbol, and we can say, okay, we're going to define this to equal this formula. And then I don't have to keep writing this formula all over again. I can just say delta t equals delta t prime times gamma. Boom. So much easier, right? Woo! All right. So one thing that is really, really fascinating to note is that as v goes to 0, delta t becomes the same as delta t prime, which makes sense. If you're moving and your speed stops, you're going to measure the same time interval. But one thing that's really, really wild, and I ran out of space here, so I'm going to erase this one because I don't want to erase my cute little circle penguin. One thing that's really wild is what happens as v increases. So as v goes to c, we actually get an infinite time interval. Delta t goes to infinity because dividing by 0 gives you infinity. And so in between, you can ask, well, the faster you go, then that means the longer the time interval is, because you're going to be dividing by, yeah, the gamma is going to be increasing as v increases. So this is pretty mind-blowing to me. I'm going to use another color here. This is pretty much the crux of relativity. So this is kind of the whole concept of like, when you get to the edge of a black hole, well, I guess that's more gravity than speed, but basically like as your speed increases and reaches the speed of light, or if your gravity is so big that effectively your time interval increases, the time interval that other people see is potentially infinite. So you would be stuck in time. Not for you. Your time clock would be ticking, because relative to everything else, you are stationary, right? It's only when we compare the two that we get these results. So that's really wild to me that I can experience something totally different when I'm sliding down the ice, glissating, if you will, or when Will Physics Penguin and their friends are sliding down the ice. They experience a different time than the friends that are stationary and cheering them on. Wild, right? Now, the speeds that you and I experience or penguins experience, it's pretty negligible. But when we're talking about satellites, which are traveling much, much, much faster than us little people and creatures on the surface of the Earth, you actually do have to take this into account. So, yay, physics, for being able to help us mathematicize the world around us and discover really wild and wonderful things, and also be able to solve problems that would otherwise be really confounding, right? Because if we were if we were trying to sync our clocks with the clock on a GPS satellite, we'd be like, wait, these are really off. What is happening here? It's ticking way slower than it should be. Well, ta-da, relativity. They're moving faster, so their time, they are experiencing time dilation. They have stretched time. Okay, so a lot of caveats here. It's like there's very specific details about, you have to have the same placement of the light source and all of that. But really, it's to illustrate that like this is a totally real thing. You can math it out, and I just love that. It's so cool. Or as my physics professor used to say, it's geeky cool. Thank you very much for hanging out with me and learning more about time dilation. Please let me know if you have any questions about this or other science, tech, engineering, and math topics. We'll see you next time.